So that was ionic compounds. What about covalent? When we have two nonmetals, we get a molecular compound. Here the electrons are shared. So what we do in Lewis theory is we represent this covalent bonding by drawing the neighboring atoms next to each other and having them share some of their valence electrons so they attain an octet for each of them. So let's look at hydrogen and oxygen. So the Lewis structure for hydrogen is an H with one dot, and oxygen, we've done a couple of times now, has 6 valence electrons, so there's the Lewis structure for oxygen. Now, oxygen and hydrogen are both nonmetals. They're not going to form an ionic compound. What they're going to do is they're going to share electrons. So you could imagine this being a nonmetal, it's out there looking to gain electrons. And the oxygen says to the hydrogen, hey, I need some more electrons. Can I have your electron there? And the hydrogen says, no way, I'm a nonmetal too, and I need to get an electron. Give me one of your electrons. And the oxygen says, no. And they have this argument, right? Two little girls arguing. And, well, what do? You share, right? So what if they share these electrons instead? Shared electrons count for both. When they share electrons, this hydrogen looks at these shared electrons and says, hey, those are mine. And the oxygen looks at the shared electron and says, yeah, but they're mine too. And so the hydrogen now claims both of those electrons. How many electrons does hydrogen want to have? 2. So he's got 2. He's happy. Is the oxygen happy? No, not quite. The oxygen has 2, 4, 6, 7 electrons. So enter another hydrogen atom. And the oxygen says, hey, will you share with me? We can both be happy if we share. Like, hey, that's a great idea. Let's do it. So this hydrogen feels like both of those electrons belong to him. Well, it's, I guess, a her, it's a nonmetal. And the oxygen claims all of those electrons. So the oxygen has 8, and each of the hydrogens has 2. And everybody's happy. Wouldn't it be great if life was that simple? All we had to do was share electrons till we had 8. The shared electrons count for both. My husband and I have 6 children. If you ask him, how many children do you have, he'll say 6. If you ask me, I'll say I have 6 children. Are they my children? Yes. Are they his children? Yes. They're shared. They belong to both of us. So they count for both of us. When the electrons get shared, we can count them twice. They can count for the hydrogen, and they can count for the oxygen. Yes?
Does that only happen for nonmetals?
This only happens for nonmetals. Metals are not good at sharing. Metals don't share. Metals say, no, just take it. And the nonmetal will say, oh, great. And when you have metals and metals together, it's a whole different idea that we'll briefly mention somewhere later in this semester. So those shared electrons count for both. And that was just a fancier picture of what I drew. So in a molecule like water here, we have 2 different kinds of electrons then. These are bonding pairs, meaning they're shared between, and it's those 2 electrons that are shared that causes the bond. And there are also unshared, non-bonding, or lone pairs. Lone pairs are a pair of electrons that are all alone. They're not between 2 atoms. They're just sitting on 1 atom. So we need to be able to look at a Lewis structure and recognize bonding pairs. These are both bonding pairs, and this top and bottom, those are both lone pairs. Now, drawing all these dots can get a little tedious. It's great on the iPad because I can make the pen wider and I can just go boink and I make a nice fat dot. When you've got a pencil or a pen, especially if it's real fine, and you just go boink, it's so small that it's hard to see. And so then you end up going like this, like this, you know, trying to make it big enough, because if you just do that, you can't see it, it's not big enough. So you have to draw little circles or something. So a lot of times what we'll do, and just to clear things up, is we'll draw those bonding pairs as lines. And another way you can think of this is, let's go back to our original thing here. Those nice fat spots, I love those. It's a little bit like this. We're just connecting the dots of the shared electrons. So each of these lines represents a pair of electrons. That's 2 electrons, one from the hydrogen, one from the oxygen, that are being shared. We talked about diatomic elements. The horses need oats for clear brown eyes business. Why do those elements form molecules? Why don't they float around as individual atoms? Well, Lewis theory explains this. Let's look at the Lewis structure for bromine. How many valence electrons does bromine have? 7. Does bromine have an octet? No. Here's another bromine atom. It doesn't have an octet either. What could they do to get an octet? They could share. So they will form a covalent bond because this is more stable for them. It's a lower energy state. When they share that electron, the 2 bromine atoms coming together, sharing the valence electron, then they each have an octet. In chemistry land, the bromine atoms are happy when they hold hands. This also predicts that hydrogen exists as a diatomic element. Okay, there's hydrogen. Hydrogen is looking for a duet, right? So if we get 2 hydrogen atoms together and they share and make a covalent bond, then we can have a duet. And we can do this actually with all of the diatomic elements. Sometimes atoms will share more than 1 electron pair to attain an octet. So let's look at oxygen. We've looked at oxygen a lot today. So here's the Lewis structure for oxygen. And here's another oxygen. Oxygen is one of those diatomic elements, isn't it? It's the oats. O for oats. Well, 2 oxygen atoms can help each other attain octets. If they share 1 pair of electrons, they're getting closer, but they each have 7 right now. And they also have this other electron over here that's unpaired. And so what they'll do is they'll share 2 pairs of electrons. And so we might draw that like this. The 2 lines, each line is a pair of electrons. There's 2 lines, so we call it a double bond. Any questions? This is a lot more straightforward than all that quantum mechanical stuff, isn't it? I love pictures, dots and lines. I can do that. So a double bond is when we have 2 electron pairs shared between 2 atoms. The double bonds are shorter and stronger than a single bond. And just as evidence of that. The distance between oxygen nuclei in an oxygen-oxygen double bond is 121 picometers. In a single bond, it's 148. So the distance between these atoms, if they only have a single bond, is longer. And that makes sense. The more you share with someone, the closer you get, right? Let's look at nitrogen. N2. There's one nitrogen atom, there's another nitrogen atom. And each of these guys has 5 valence electrons. Can you see where this is going? They could share this pair, and that pair, and that pair, and in doing that, then they both have 8 valence electrons. Because they were both short 3. And so when they share, each electron you share, it's like you're gaining an electron. So we would normally write that as 3 lines, each of these lines representing a pair of electrons. Or if you prefer the connected dots idea, it would be like that. So this nitrogen counts all the shared electrons. These are the bonding pairs, and these are its lone pairs. And this one counts all of them. And they each feel like they have 8 valence electrons. Yes? So this is a triple bond. So this is like a picture of me and my husband because I'm sharing those 6 children. So triple bond, 3 pairs of electrons are shared. And as you can imagine, that triple bond is even shorter and stronger than a double bond. If we look at nitrogen, the triple bond length is 110 picometers, a double is 124. So because nitrogen has this triple bond, when it makes a diatomic molecule, that triple bond is very strong. That makes nitrogen a relatively unreactive element. Nitrogen gas doesn't burn. Oxygen gas burns, hydrogen gas burns, but nitrogen doesn't, because they're just pretty much stuck together.